Today, we'll talk about butterfly bots, create smart textiles, and check out hydrogen solar power. This is NSF Science Now. Borrowing from nature, NSF-supported North Carolina State University engineers have developed a lightweight, energy-efficient swimming soft robot that looks like a manta ray and moves like a person swimming butterfly.
But our bot is the first swimming robot actually can swim like a human butterfly stroke. And then the key is from the bicycle wings. You can see that the wings can not only rotate, but also flap.
The bot's swimming power comes from its wings, which are bistable or have two stable states, like a snap hair clip. The clip is stable until you apply a certain amount of energy by bending it. The clip snaps into a different but stable shape when the energy reaches critical mass. Most attempts to develop flapping robots rely on motors to direct power to the wing. By using bistable wings, the team can simplify the design and lighten the load.
So we pump the air into it's a central bidirectional soft body to let it to bend. The bending of its soft body will trigger the flapping of this bistable wing. And at the same time, we added an extended fin to further amplify its flapping motion and interactions with the water to let it to achieve a very fast speed and high efficient at the same time.
This butterfly bot is fast, with an average speed of 3.74 body lengths per second.
If we compare this speed to the marine animals, it's going to be close to the penguins. The penguin can swim at a speed of 4 bodies per second, so our soft robot is very close to that. In addition to the fast speed, also, it's energy saving mode. So that means when it swims so fast, but actually it consumes very less energy, so it can swim longer and also faster.
The team developed 2 prototypes, one for speed and one for maneuverability. The first has one drive unit, its soft body, which controls both its wings simultaneously, making it lightning fast but unable to maneuver. The second bot has 2 drive units connected side by side, allowing users to manipulate the wings independently, enabling it to corner like it's on rails. These soft swimming robots could have applications ranging from ocean exploration to oil spill cleanup. While more work is needed to perfect this butterfly bot technology, the team hopes to develop an untethered autonomous version next. Today, over 32 million workers are exposed to toxic fumes in the workplace. Gases like nitric oxide and hydrogen sulfide are found in a wide array of occupations, including mining, steel production, oil refining, and even construction and plastic manufacturing. Chronic exposure can lead to respiratory problems, cancer, and even death. That is why researchers at Dartmouth College, armed with both an NSF Career and EPSCoR awards, have created a copper-based smart textile called SOFT, Self-Organized Framework on Textiles, for chemical sensing, filtration, and decontamination.
We have created a new method for making electronic textiles. These textiles can sense, filter, and detoxify small reactive gases such as nitric oxide and hydrogen sulfide.
The team discovered that using copper to create specific patterns layered into fabrics like cotton and polyester allows it to fill in the tiny gaps between threads, easily converting poisonous materials into less toxic substances, all while withstanding everyday use.
Remarkably, these textiles are extremely robust and can maintain their function even through tests of abrasion, ironing, and laundering.
The new method's versatility and durability would allow the framework to be applied for specific uses and in more precise locations, such as on protective clothing or as a filter in a particular environment.
We believe that this approach may pave the way to enhance smart personal protective equipment and healthcare applications.
The fossil fuels, including coal, oil, and natural gas we rely on daily, release harmful greenhouse gases into the atmosphere. Finding a safe, efficient, cheap alternative is challenging, but hydrogen may be the answer. NSF-supported engineers at the University of Michigan have developed a new kind of solar panel that harvests the sun's energy to separate hydrogen molecules from water. This process is similar to, but more efficient than the natural photosynthesis process, reducing our carbon footprint.
We have identified several important steps to break the efficiency bottleneck. One important aspect is to harvest the previously wasted infrared light of the solar spectrum.
The system harnesses the higher energy part of the solar spectrum to split the water. The lower part of the spectrum provides heat upwards 167 degrees Fahrenheit, warm enough to favor hydrogen production.
At elevated temperatures, the hydrogen-oxygen recombination can be suppressed, so that will give us higher efficiency solar hydrogen generation. Currently, we are at a little over 9%, very close to 10% solar to hydrogen efficiency.
This efficiency is made possible by the uniquely designed semiconductor, which can withstand high temperatures without degradation. The team hopes to improve the system's efficiency, leading to future commercial production to provide clean hydrogen for transportation fuels, electrical energy, and heating and cooling, while minimizing greenhouse gas emissions.
The materials we use, gallium nitride silicon, can also be produced at large scale, and we can leverage the current infrastructure for low-cost green hydrogen generation in the future.
For more information about these stories, visit us at nsf.gov. This is NSF Science Now. I'm Dina Headley.